All right. So thank you everybody for joining today, and please feel free to interrupt the speaker. This is a regular Zoom. We are very glad to have today Arsalan Mousavian. He is a researcher at NVIDIA. He graduated with GRASP alumna Jana Kosetska at the George Mason University. And before that, he had studied at the University of Tehran. He had many industrial positions, including the Google Street View and Brain Group and Zoox. And he's going to talk to us about robot manipulation of unknown objects. Thank you very much for joining us today, Arsalan.
Thank you. Thank you for the introduction. So today I'm going to talk about robot manipulation of unknown objects using learned object-centric models. So first, let's look at the robot hardware today. So we have these like amazing platforms that they can jump, run, dance, and do all sorts of crazy things. And we also have like very sophisticated systems for teleoperating the robot. So here you can see like Jeff Bezos wearing these haptic enabled gloves, and the robot fingers also have like tactile sensors, so he can easily control the robot and stack these cups on top of each other. In our team, we also have like a similar setup, but without any haptic feedback. So we have this like camera rig, and we do hand pose estimation, and we transfer it to the robot. And we can do like complicated tasks, such as like sliding the credit card on the surface, or like opening a box by just getting the visual feedback from the human, and also taking out like a bill from a wallet. There are also like very sophisticated hardware platforms. So this is like a handy robot from Samsung. So they show that they can do these tasks by doing like teleoperation, which means that the robot hardware is like capable. But we are still far from having robots in our home. And in the real world, like even in industrial setting, there is a different story that, like for example, in the beginning, Tesla went all in on using a lot of robots for building Model 3, and they had to scale it down. And then Apple also explored manipulation, like assembly tasks, using robots, and they realized that robots are not capable in doing complicated tasks. And this basically presents like an opportunity for researchers to work on these data-driven methods to basically fill in the gap. So there are different ways of different approaches for solving these like manipulation tasks. The first category is the object agnostic model free methods, that they are trying to just learn a mapping from sensory data to actions. So the advantages of these methods is that they have minimal assumptions about the board. So you basically say that I'm interested in the mapping from the raw sensory data to action. And the whole system is a big monolithic model, so you don't need to spend a lot of engineering on integrating different modules, but you need a lot of training data to be able to train these models. And they usually like have very poor generalization to new environments and new objects. And most of the successes on these like model-free object agnostic methods are on short horizon tasks. And the other thing is that there is like no compositionality. So you cannot really, like if the task changes, you need to retrain the model, retrain the model again, and you cannot really use the models in different tasks without any training. On the other side of the spectrum are the model-based methods. that basically you say that I have the 3D model for all the objects in the board, and I will just do pose estimation and estimate the rotation and translation of the objects with respect to the camera. So basically, once we do a state estimation, we can represent the board with just some 60 poses. And then we can use like classical methods in task and motion planning to basically solve like long horizon tasks. But these methods also have some limitations. So the one limitation is that they only work on known objects. So if there is an object that you cannot, that you didn't account for it, or you don't do a state estimation for it, so you cannot react to it. And if there is any error in a state estimation, it accumulates and it makes the system brittle in the real world. And the other thing is the scalability of the state estimation methods. So at least today, there isn't like any pose estimation method that has like one model trained for like thousands of objects. And on the planning side, because there is no learning, you need to implement a lot of things manually. So in this talk, I want to present like an intermediate step between totally model agnostic way and the model-based methods, and I refer to it as model-free object-centric models. So in this approach, we kind of say that we represent the scene with the object instance segmentation. So we have an RGBD scene, and we can segment out the objects, and we have these high-level tasks that are again object-centric. So the task can be like shuffling some objects to get to some final configurations. And then you have these object-centric controllers that they use like models that they use like object-centric models. And these object-centric models can be like for different tasks. Like for example, one model can be used for grasping, one model can be used for like collision checking. So like simple tasks, but they have to be relative, they have to be like really object centric. So everything should be computed with respect to the objects. And I will show with this kind of with this approach, you can actually get generalization to new environments and objects, and you can reuse these models across different tasks, and you can also train them much easier than the other methods, and it can also be trained separately and also fine-tuned after the integration. So more specifically, I will talk about how to segment unknown objects in the scene. And like with objects, in order for the robot to interact with the objects, you can the robot either grasps the object or like pushes the object around. But in this talk, I'm going to talk about grasping. And then at the end, I will talk about collision checking and motion planning for unknown objects and scenes. So let's first talk about unknown object instance segmentation. So we want to teach the concept of the object to the model, and to do that, we need training data. So one source of data can be like internet images, but they are not really suitable for object instance segmentation because you need to have segmentation annotations. And there are also a lot of vision data sets that have like these outdoor scenes, or when they are inside, they are like from very far distances. So they are not really like the tabletop settings or like close range setup that the robot interacts with other objects. So instead of using real images, we basically use the synthetic data. So we basically put random objects in random orientations in some synthetic scenes, and we can render RGB, depth, and instance labels for this just from the simulator. And then we basically we basically train a model that takes in the RGBD image of the scene and it predicts like an embedding for each pixel. And the loss function that we have basically tries to push the embeddings of the pixels for the object, pixels of the same object toward each other. And if two pixels belong to different objects, it wants to push them away from each other. And basically, so we want to kind of learn this high dimensional embedding that then in the test time, we can basically cluster them and segment the objects. So here you can see like an RGB image of the scene. And
Arsalan, 1 second. I mean, the last layer of this unit architecture is still an image. How do you get like, is this image itself the vector in the embedding space, or?
yeah. So each pixel is a vector. So it's like a 32-dimensional vector for each pixel.
And the points you're showing there are pixels?
No, these points are like
the whole image.
These are the feature. These are the dense feature maps. So this is in the embedding space. It's high dimensional. It's not just 2D.
But is one point per pixel or per image in the embedding space?
So you will get an embedding per pixel.
Embedding per pixel, okay.
Yeah. And then you basically have this loss that pushes the embeddings of different objects far from each other. And then during testing, you can basically do clustering on these features. So this is like the visualization of the feature maps. And after clustering, you will basically get the segmentation for these objects. So now that we know how to segment unknown objects in the scene, I'm going to talk more about the grasping unknown objects. So let's first give some comparison between model-based grasping and model-free grasping. So one approach is that, so let's say in this image, I want to grasp the blue picture in the image. And because this is model-based, I assume that I have the 3D model for this blue picture. And then we can use our like favorite pose estimation method to get the relative rotation and translation of the object with respect to the camera. And because we have the 3D model for the objects, we can also annotate it with the grasps. And we basically transform these grasps using the predicted object pose. And then basically the robot goes to that final pose and closes its finger, and then it can basically grasp the objects. So in the model-free grasping, we want to basically directly go from the image to the, and by image I mean like RGBD image to the final grasps. So these grasps are represented by 3D rotation and 3D translation. So they have like 6 degrees of freedom, and the space is quite challenging. So one simplification that people did for grasping was to only consider planar grasping. So instead of considering the full 6 grasping, you only say that I'm interested in the grasps that are perpendicular to the surface. And you can basically represent it by an oriented rectangle. And you represent the rectangles by the center location of that rectangle and the orientation of that rectangle. And in order for this representation to work, you need to have the camera roughly perpendicular to the surface, and that also makes the effective workspace of the robot very small. So here in this work, the workspace is very small, and in the other work from Google, they can only handle objects inside that tray. But we want to fully utilize the full space of the SE3 transforms for the grasps. So we define the grasps in the coordinate of the object point cloud. The origin of this point cloud, the origin of this coordinate frame is at the center of the object point cloud, and the rotation of the coordinate system is the same as the rotation of the camera. And what we are interested in is to find the the SE3 transform for this grasp, so that the gripper just goes there and closes the finger to grasp the object. So we introduced 6 of GraspNet, and so basically the input to the model is the RGBD image of the object, and using the segmentation and projective geometry, we can get the object point cloud for that object. And
Sorry, how do you get the point cloud here?
So we have the intrinsics from the camera, and we have the RGBD image. So we have the per pixel depth from the camera as well. So you just project them to 3D and you will get the point cloud. So
Okay,
this is just
it's better.
pure.
It's better to say input RGBD image, because there are 1,000 papers on getting from RGB, not RGBD, to the representation that you have here. Okay.
Yeah, I will update it. So the input is RGBD, and basically the first part, which is the grass sampler, is basically a generative model that takes the point cloud of the object and proposes different grasps in the object point cloud frame, the frame that I mentioned in the previous slide. And but not all these proposed grasps are good enough. So we have this second model, which is basically a classifier that predicts the success of each grasp, and then we also refine the predicted grasp iteratively. So for the generative model, we use a conditional variational autoencoder, and here you can see how grasps would change by changing the latent value that is input to the decoder of the variational autoencoder. So this is how the grasp would evolve. And
So this is input is the image in the variational encoder, and output is an SE3 value.
yes. So the input is the point cloud, is just the point cloud of the object, not
The
the
point cloud.
background.
Mm-hmm.
Yeah. And the other input is the latent value, which during training we minimize the KL divergence so that it has this Gaussian distribution. And so you basically feed in the latent and the point cloud, and for different latents you will get the different grasps. And this is basically how the grasp would evolve by traversing a line in the latent space. And we basically trained this with the simulated data. So we trained it on 126 mugs, bowls, bottles, boxes, and cylinders. And we simulated a lot of grasps in the simulator to get a set of graphs for each mesh. And then we take these meshes, render them at random poses to get the point cloud. And because during training we have the model for all these objects, we can transform these grasps accordingly. So we have this huge training data for like pair of point clouds and grasp transforms in that object point cloud. And the nice thing about training with like point cloud data is that it transfers really well to the real world without doing any domain adaptation. And recently we ramped up our effort on these training data. So we introduced this acronym dataset. So it has 17.7 million grasps, 8,800 meshes from 262 categories. And we also provide realistic object scales for each of these meshes. And the nice thing about this dataset is that basically in all of the works that I'm going to talk today, if we just train the same method on acronym dataset, we get significantly more robustness and generalization. And the dataset is also available publicly. So here is the qualitative results on grasping single object using GraspNet, 6-staff GraspNet, and we didn't include any of these meshes in our training. So these are like completely unseen objects. And so this is the result of the training. This model is trained on the smaller scale data set that I talked about in the previous slide. And we also recently used it in other applications. So we didn't do any retraining for this task. So this task is that the object wants to take the object from the human hand. And the only thing that we changed was that we changed our instance segmentation to basically segment the object that is in robot's hand. And you can see like it can even handle like deformable objects, even though we didn't really train on any deformable objects. But one thing that is missing is that the robot is not going to be only interacting with one object in the board. So robots are usually interacting with like cluttered environments. We basically extended the 6-staff GraspNet to the cluttered setting. So let's talk about this scenario. So here we have the scene, and we want the robot to basically grasp the yellow mustard bottle in this scene. So and we also have the object instance segmentation for this scene. And this is again RGBD image. So we have we always use them for all the methods that I'm presenting today. So we project these to 3D, and we basically only consider a small bounding box around the target object, because that's where the object is, and we want to basically avoid collisions with the objects that are close to the target object. And then basically we crop the point cloud of the scene to only see the point cloud of the scene around the target object. And we use basically GraspNet to generate grasps for the target object. And we also have this like additional model that reasons about collision of these grasps with the other objects that are visible in this scene. So this only reasons about the collision of the gripper with respect to the objects that are next to the target object. And basically that's how we extended it to cluttered scenes. And if you can reason about both grasping and gripper collision with the objects in the vicinity of the target object, you can do some interesting stuff. So for example, here, let's say we want to pick up this white mark, but it is kind of, the other objects are kind of blocking the gripper to get to this object. So what we do is that we generate grasp for the target object, and we check the collision of the grippers with the other objects in the scene, and we can do that because we have the instance segmentation of the scene. And then we can find out which object is the one that is most blocking, and then basically the robot changes the target from the white mark to this sugar box, and it moves it out of the way, and then it comes back and then realizes that it can grasp the object without any problem, and then it basically comes back and grasps that white mark here. And we also did quantitative comparison in real world with the baseline, and the baseline here is that we just use the 6-staff GraspNet, and instead of like having a learned model for checking collisions, we just do voxelization and reason about collisions, but that performs worse than the learned model. And one of the reasons is that when the objects are packed together, there are a lot of occluded points that they are not visible in the scene. And then basically you don't put any voxels in those regions, and then you will basically get colliding grasps. But there is a,
Arsalan, one second. In these numbers, can you tell us in both cases, does it fail in the segmentation or in the grasp
so
regression?
I will get to the segmentation, but this is like the performance of the whole system. In
Yeah, yeah.
the
But
paper,
why does it fail?
uh, so 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 here the failures are in two categories. One is that if the grasp is colliding with any other objects in the scene, then the robot will basically make a mess. So it will collide with those objects, and it will remove them. The second reason for failures is that sometimes these transforms, uh, like the way we simulate the physics in the for the acronym dataset doesn't necessarily reflect with the friction coefficient that is happening in the real world. So we randomized all of that during our training, but there are some graphs that are tricky to succeed in the real world, but in the simulator they work perfectly. So that's
But
also
the vision is perfect, right? The computer
the,
vision is perfect.
no. This so the predicted grasp can be wrong because either the data is not good, or has some limitations, or the model is not able to fully utilize the knowledge from the data. And the other
But
kind of
let's say the instance segmentation would be perfect. It would be like from the training data set with all use all the ground truth for the instance
mhm.
segmentation. How
so
much would be the performance then?
so I didn't put those results here, but we have them in the papers, in the paper. So we did this like simulation experiment, which is with a grain of salt because the physics engine are not completely matching the real world, but we have like comparisons with the perfect segmentation. So the reason I don't have like an exact number is because in the simulator we evaluate all the predicted grasps, and so we are not just executing the best grasp. We are executing all the grasps and evaluating them, and so we create this like kind of precision recall curves. I wish I had those plots here, but they are in the paper. We don't do like equivalent of this to, for example, to do like table clearing task and these kinds of things in simulator. We just evaluate all the graphs to make these like precision recall curves. Um, but you also brought up some points about the instance segmentation that I wanted to talk about it. So one uh, there are like two limitations with this work. So one limitation is that if the instance segmentation is not perfect, which is the case for this white bottle on the left, you basically won't get any grass on the top side of this because the grass sampler doesn't even see any of these points at the top. And the other limitations is that we generate a grass for the target object in the absence of table and the environment surrounding it, and then we do the filtering. And because of that, like for example, if you have like a thin object like this, and you generate like, let's say, this grass for it in the absence of the table, this grass will be filtered out after you put it on the table, because the first part was like agnostic to the point cloud surrounding the object. So we address these limitations in our recent ICRA paper. So we introduced contact grassnet. So in contact grassnet, we want to predict grass transforms for all the points in the scene. And similar to before, we also do object instance segmentation, but we don't put instance segmentation in the critical path for generating the grasps. So basically, the model generates graphs for all the points in the scene, and then we associate these grasps to objects based on the proximity of each grasp to closest segmented point cloud. So for example, we say that for these graphs, these are closer to this segment here, so they belong to this specific object. And as a result, we are less sensitive to object instance segmentation issues. So I'm going to
So
give,
one second. What do you mean creates grasp? These are like feasible grasps. I mean,
yes,
anything can be a grasp. Feasible grasp
yeah,
without
yeah,
collision.
yeah,
Without collision.
exactly,
You mean? I
exactly,
see.
yeah, yeah. So basically, instead of having that pipeline module that we generated graphs for the target object and then we filtered everything out with another model, here we do everything in one take. So we say that we just want the collision-free graphs, and we give like the scene point cloud, and we want to basically get those graphs. And go ahead.
And this is collision free at the end pose or during the whole trajectory.
Uh, I This is a very good question. I will get to it later, but
Okay.
this is just for the gripper. So here collision free means that only for grippers, similar to the previous grasping work. And so oh, and then another thing that I wanted to mention is that we still do the cropping as before. So for each of these objects, we make a loose bounding box, and we generate graphs inside each of these cropped point clouds, and then we aggregate everything together, and then we will get something that you see here. But again, the nice thing about it is that we don't put instance segmentation in the critical path. And we also, so now that I talked about how that we need to generate graphs for each point in the scene, we want to we have to define the coordinate frame for these graphs. So we define this like 4 degree of freedom representation for graphs that is like hinging on the contact points. And our assumption is that if you have a suitable grasp, it should have most of the time it has at least one visible contact points, and you can see the contact point here shown in with the circle. And now that we have the contact point, we have to predict two directions, which is the approach direction for the gripper and the direction for the baseline of the gripper. And uh, we also need to know what is the offset from the contact point to this point here, because again we want to represent the transform for the gripper. So we have to somehow find this relative transform from contact points to the gripper points. And this width is we basically use half of it as an offset from this point, from these contact points to here. And we have this other fixed parameter, which is d, which is the depth of the gripper, and this is constant. We just get it from the geometry of the gripper. And here is a visualization of the suitable and unsuitable contact points for a wine glass. And so basically, let's say we have this grasp. The contact point for it would be this point. So we shoot a ray from one finger and intersect it with the mesh of the object, and that's how we get the contact points. And we trained the whole thing with the synthetic data. So the meshes and grasps come from the acronym data set, and we can arrange them in the simulator. And we can also remove the collision free. We can also remove the colliding grasps using like any computational geometry libraries, because we have the 3D models during the training. So now we have these scenes with meshes at random locations and grasps associated with them. And then we render these scenes at with random camera poses, and we feed them to the network. And the network predicts three different things. So the first thing is the contact scores, which is basically a probability saying that whether that specific point is a suitable contact point or not. And we predict the rotation of the grasp through the approach direction and the baseline direction. And we also regress the grasp width. So we have three loss functions. The main one is basically saying that I want to minimize the weighted distance of the predicted grasps with any of the ground truth grasps. So if a prediction is close to any ground truth grasp, we want to encourage the network to maximize the confidences. And if the error is very large, meaning that the grasps is either in collision or not successful, we basically want to minimize this confidence. And we also have two auxiliary loss functions. One is the binary cross entropy on the contact scores, and the other one is a regression loss for the grasp width. But we put most of the emphasis in the training on this like weighted distance, weighted average loss that I mentioned here. So this method achieves like a 90% success rate in the real world, and it basically so it can handle the thin objects, it can handle like the imperfections in object instance segmentation, and we also evaluated it on very similar scenes that we tested this cluttered GraphNet. Of course, we cannot like make them absolutely perfect because like I just placed these objects to visually look similar, but in order to do that, and then we did that, and we got this like 10% improvement in the real world. And we also in the paper we have comparisons in more constrained setup in the simulator with perfect instance segmentation and everything, and you can check out those comparisons as well. But in all the aspects, contact GraphNet is the best grasping method that we developed in our group. So far I talked about uh, how to segment objects, how to generate grasp for them. But the third thing that Kostas also asked questions about it is how to do like the motion planning. So let me give a formal definition of motion planning in case you are not familiar with it. So in motion planning, we want to find a sequence of valid and collision-free configurations for the robot that basically gets the robot from configuration A to configuration B. And one of the things that we need to do in motion planning is to check for collisions. And there are different methods for doing that. So one approach is to do it in model based. So we say that we have the 3D model for all the objects in the board, and we do a state estimation, and we can basically check for collisions because we have the meshes for the robot, meshes for all the objects in the board, and we also did the calibration between the camera and the robot. But that has the limitation that you need to know the 3D model for all these objects. So another way for doing collision checking is to approximate the geometry of the scene through voxelization. So you basically voxelize the point cloud of the scene, and you will get this like coarse voxels. But it has this limitation that you need to have multiple cameras to have the maximum coverage and minimal occlusion, because if you don't see anything, you won't put any voxel for it. And the other approach is that instead of voxelization, you just take the point cloud of the scene, and you create the mesh from that scene point cloud and compute the SDF value or just do collision checking. But we want to do it for unknown objects and unknown scenes. So here, I'm just showing a simple example that we want to have. We want to move this cylindrical object from the left side to the right. And as you can see, the robot has to reason about collision of the robot links and the scene, and also the objects and the scene. And so we are going to tackle this problem of like collision checking and motion planning for unknown objects and scenes. So so this is basically the point cloud of the scene from the previous video. And let's say I want to reason about collisions for a future configuration, and I need to reason about collision for the robot meshes and also the object that is in gripper, so which is shown here. And so the first thing that we do is that because we did the robot to camera calibration, we can segment out the robot by just doing nearest neighbor in the point cloud space, and we can remove the point cloud of the robot point cloud. And now we have this scene and this configuration that we want to check for collision. And we can represent the robot by its meshes. So this comes from the URDF model of the robots that comes with each robot. So this is like a very relaxed assumption. And then we can represent each of these robot links with the point cloud for those meshes. So now basically we represent everything in the point cloud. So the object point cloud is already in the 3D space, and the robot meshes are also in the 3D space and are represented by the point cloud for each mesh. So now let's say we want to do collision checking. So we basically check for collision of each of these meshes. So we have this like collision queries that can be either robot point cloud or the point cloud for different links of the robot. And each of these queries are basically comprised of the query object point cloud that we have from the that we have, plus the transform that we get from the forward kinematics of the robot. So we have a bunch of SE3 transforms, and the objects are represented by point cloud. So recently, there are a lot of works in computer vision community in reconstructing the scenes from partial point clouds, but they have some limitations. So either the inference time is slow, or they have like very poor generalization to new scenes. So basically, if you look at like deep SDF, they trained models on a specific category and they tested on that category. And approaches like NERF, they train a model for a specific scene, they get amazing results in different viewpoints, but it doesn't really generalize to a new scene. But in robotics, we are interested in fast inference times and like generalization to unknown scenes, because we cannot expect the robot to train on every scene that it's going to encounter. So we introduce scene collision net, which is a very efficient architecture for processing a large number of collision queries. So it can basically process 500,000 collision queries in one forward pass, and it only takes 0.1 second. So I'm going to talk about how scene collision net works. So the input to the scene collision net is the point cloud of the scene. And we first process these point clouds and pass them through an MLP to get some point features. And then we voxelize the scene, And this voxelization, these voxels are very coarse. So each of these voxels are between like 15 to 20 centimeters each. So they are not like high resolution. And we basically do a max pooling on the pair point embedding to get the embedding for each of these voxels. So now we have this coarse voxel representation for this scene, and inside each of these voxels is basically a feature embedding that represents the geometry in that voxel. And then we use this unit architecture to get higher receptive field, higher larger spatial support for each of these voxels, and make the voxels even more coarser. And now we need to process the query objects. So as I mentioned before, we represent the query objects by their point cloud. So this can be either point cloud of the object or point cloud for each of the robot links. And then we use pointnet++ to basically get embedding for the object point cloud. And the last part that does the magic of classifying this insane amount of collision queries is this small classifier at the end that basically takes in the object embedding that we computed here and concatenate it with the corresponding voxel embedding from this coarse voxel representation. And we also normalize the rotation and translation of the queries with respect to each voxel. So basically this MLP is very lightweight and can have like a very large batch sizes. So in practice, we run the scene encoding only once per time step, and we run the object encoder for each of the objects once per object. And the only thing that runs a lot for all these collision queries is this small classifier at the end. So let me show you how we use these scene collision net for generating collision-free paths in the board. Before that, so we also did a comparison in simulator and compared it with the classical methods to do like March cube and doing like SDF or like computing collisions with FCL library. And we also have implemented it in multiprocessor with multiprocessor to make sure that we have the optimal performance from the CPU implementation. But scene collision net is still an order of magnitude faster than any of the classical methods, which can simplify the motion planning problem quite a lot. So now let me show you how we do motion planning in unknown scenes and unknown objects. So let's say we want to move the cylinder object from here to this purple region on the right. So we first generate like different trajectories in future for the robot. So let's say this is like one trajectory, and then we check for collision of that rollout, and then we get this we get this like trimmed version of the rollout, and then we generate like different trajectories in future. So if you look at all these trajectories, this is like the visualization of like 100 trajectories in future.
How do you generate this collision free? Are they collision free, these trajectories, or?
No. In the beginning, they are not collision free, but then we use scene collision net to trim them and remove and basically trim these trajectories at the points that the scene collision net thinks they are in collision. So you can see like the difference here.
Why don't you use something like RRT here to produce trajectories so that you are more efficient?
So one thing is that because scene collision net is like highly parallelized, you want to basically uh, um, leverage the fact that sync collision net can process a large number of things at once in parallel, but RRT has this like sequential thing that you need to grow the tree. So you can also make some changes to like distributed RRT so that you can grow it in different ways. But again, you have to deal with the problem that you have this tree that is shared among all these like different rollouts. Um, Here we are doing it in a different way. So we sample a lot of trajectories in future. We check their collisions, and and the nice thing about it is that we can compute, we can aggregate all these poses together and batch them and have these like insanely large batch sizes and just run one forward pass to basically trim these rollouts to get this. And the next step is that we are scoring each of these rollouts. And the scoring is done based on the distance in the configuration space from the current location to any of these points on the right. So, and the rollouts are highlighted with the scores that we are getting. And then the robot basically executes the best action, and then we repeat the process at the next time step. So in a sense, our method is like fully reactive. So it kind of it takes new observation at each time step. Uh, rolls out promising trajectories in future and executes the best one. And because we constantly get these observations, uh, uh, we can also do we can do like more interesting tasks that I'm going to show now. So here is like another task that the robot needs to pick up these objects and put them in this like green zone on the right. And this green zone is, by the way, is not in the image. So we just photoshopped it for visualization. We just manually specify this placing region, and the robot basically grasps these objects and places them into this placing zone. And we use this MPPI setting, the rolling out trajectories for both grasping and for placing. The only difference is that in grasping, the cost function is the proximity to any of the grasps, and in placing, the cost function is proximity to any of the placement locations. So basically, we use the same algorithm for picking and placing. And because the system is reactive and it constantly takes the point cloud of the scene, it can react to the changes in the environment. So here we introduce this dynamic object, and the robot basically reacts to it and places it in another collision-free location. And we can also do it for grasping, that initially the robot wants to uh, this green cup is at a different location, and then we move it in the middle, and the robot basically uh, follows it and grasps the object. And we are using basically the instance segmentation that I mentioned in the beginning. And for grasping, we are using contact GraspNet. And for planner, we use MPPI that uses this scene collision net that I just explained. So this is an ongoing work, and this is like under review. I'm not going over the details. I just wanted to give like high level overview of like how we can tackle tasks with the object-centric models. So here the task is object rearrangement. So we start with an initial arrangement of the objects. These are all unknown objects. And we want the robot to basically achieve the same configuration that is given as target image. So what we want to do is that we want to have this very high level task planner that doesn't reason about low-level actions, but only cares about which object to select and where we should put that object. And then we feed these informations to the MPPI and grasping and instance segmentation to basically grasp these objects and placing them in those areas. So here is just a, qualitative example. So you can see like the robot basically kind of gets to that final configuration by reasoning just about the object locations in the target environment, and we are still working on it to make an improvement. So this is under review, so that's why I'm not going over the details of this work. So in conclusion, hopefully I convince you that object-centric models are very promising for manipulation of unknown objects, and these models can be shared across different tasks. For example, like in the object handover, in the robot object handover project, we didn't need to do any retraining for grasping module. For all the tabletop scenes, we reuse the object instance segmentations, and each of these models are also generic enough so they don't depend on requiring requiring the exact 3D model of the objects. And another thing that I wanted to mention is that in computer vision community, there is this big emphasis on just doing things on just RGB images. But if we have the depth images, I think they improve the performance for 3D reasoning quite significantly. And another thing that I wanted to mention was that is that if we train for for each of these subtasks directly, we can get better generalization and more robustness. For example, let's talk about grasping. Like we can say we do pose estimation and then we use pose to get the grasps. But this introduces this problem that if your pose estimate is not accurate, your grasp will also be not accurate either. And or like for if you wanted to do collision checking by reconstructing the scene instead of just doing collision checking directly. So you would basically reconstruct the SDF of the scene first, and then you would query for collisions. But and if you have any errors in the scene reconstruction, that would also translate to the errors in collision checking. But we showed that with scene collision net, if you just train on the final task, you will get much better performance. And I wanted to thank my amazing collaborators at NVIDIA and also at UW and our interns that we are working with them on different projects. So we released the code for object instance segmentation and for GraphNet, and we are also planning to release the contact GraphNet and the scene collision net very soon, definitely before ICRA. So feel free to check them out and reach out to me if you have any questions. And if you have, I'd be happy to take any questions if you have any questions about the talk.
Thank you, Arsalan. Very interesting. Folks, can you ask questions? I have some, but first you. Any questions? All right, I can start.
Yeah.
I mean, before like 20 years ago, putting the word object-centric wouldn't make any sense because everything was object-centric. How are you gonna do? You're grasping something. It is an object.
Yeah.
I mean, even in psychology, if you talk about grasping, unless we're talking about an infant who is learning how to Otherwise, everything is really object grasping. But that's probably the best comparison that for an infant is not clear. Um, so what is non-object centric?
I will show you. So, um, so for example, here the task is not to grasp any specific object. So it is saying that given the scene, I want to grasp any object in this scene on this tray. Like the model doesn't have like any notion of the objects, so it basically says that, oh, so this is the RGB image. I'm just interested in getting some grasp transforms to grasp any object in the scene. So you don't care about like which object to pick. But in everything that I showed, you care about like which object to pick, and as a result, that's why I called it like object centric. And there is also uh, so this DexNet also is like is not object centric. So if you have like the depth image of the scene, it generates grasps. It generates grasps for anything in that scene, and they don't reason about like the objectness or anything like that.
Mm-hmm. And how that's I understand now what you mean. How much augmentation do you need on, like in the acronym data set?
Mhm.
How many camera viewpoints do you need?
So the nice thing about acronym dataset is that it has only meshes and grasps, and you can generate infinite amount of training data by just rendering them. Like
Oh, I see. I
we
see. I
basically
see.
do online rendering. So
Yeah,
here.
I understand. But in general, how many, like, you still observe, even if you have depth data, you
Mhm,
still observe from a viewpoint. And I'm not talking so much about rotation invariance, but I'm talking more about really capturing things that are occluded, right? So because
mhm.
like the handle of my cup is not visible from every side.
Yeah, yeah.
So how many views do you have to change in order to do that?
So
Do
during
you do
test
it
time,
during training? During training, do you really like sample a sphere of viewpoints, or what do you do?
so so the way we do it, again, we generate the data online. So the more you train, the more new data that the network sees. So we always sample like for GrassNet, we sample uniformly in the sphere around the object. And for the contact GrassNet, we let's say this is the scene with the object, and we just move the camera around it,
I
and
see. Okay.
we basically have all the occlusions and everything.
Hmm.
I have
Other questions, Edward?
um, have you thought about how to incorporate like deformability or objects that are not well represented by object representations like sand?
Yeah, so that's a very good question. So far we have only considered like the rigid objects, and as a byproduct our models would work on deformable objects like for grasping, but we didn't reason about deformations. uh, for um, for things like sands, like there are other people in our group that are working on those kinds of material. There the challenge is that you cannot really pinpoint like one sand, like there is like a pile of sand, or you have to basically provide like segmentation for those objects. But I think given high fidelity simulator for those kinds of objects and segmentation of let's say sand, you can I think you can train models not in this way that I talked about, but you can come up with ideas that would work on the segmentation space of the scene. Does it answer your question?
Yes, thank you.
Anybody else? Georgios? No question to your classmate?
I'm already very familiar with his work, and I can
That's
ask
why.
him.
That's why you should ask him the most difficult question.
I can ask him offline, so I don't want to take the time now. Yeah.
All right. Okay, that was very interesting. And I was already like messaging several people about how to address something in a different way. And that's the success of a talk. If you inspire ideas, Arsalan, thank you very much.
Thanks for having me. I really enjoyed.
And I know that Bernadette will join your lab for an internship.
Yeah.
Yes, very excited.
And,
Yeah, looking forward to it.
we're gonna stay in touch.
Yeah.
All right. Thank you
Yeah.
everybody for joining. Have a
Thank
nice
you very
weekend.
much, Arsalan.
Thank you. Thanks for having me. Bye.
Bye-bye.
Bye. Bye.